In this video, we're going to work out the cantilever beam problem for meshing and convergence using PATRAN. So I have a new, I would like to make a new model here. So I have an example model database which is open. And I go back to setting up the model one by one using the different flow of making a finite element model. So to make a one-dimensional geometry, I just need to make a line. So I can create a curve directly for 2 points, and the starting point for the curve is the origin 0, 0, 0, and the final point is 100 millimeters away in x, and that's where my beam arises. Then I move on to properties. In properties, I can create an isotropic material. I'll just call it aluminum. You can give it any name you like, as long as you remember what it actually means, what are the properties in it. I'm going to put in the properties given to me in the example problem. I hit apply, so the material is created. After the material property is created, I want to create a one-dimensional beam property, which you will find over here. Now, once you go to create a 1D beam, the first thing you need to do is give it a name. So I know it's a cantilever beam, so I'll just call it a C beam. Then following that, it's a general section standard formulation beam. So I'll go to input properties. And under input properties, it says what is the section name. But actually, I haven't selected a section yet. I haven't made any section. So here, if I click, this is a shortcut to existing beam sections that I have created. So the first step, therefore, would be to create a certain beam section, which comes under create sections here. So if you open it up, you get standard beam library. You have many different cross sections you can use. The one we need to use is a standard rectangular cross section. So I'll give it a name. I'll call it rectangular. And the width is given to us as 5 and the height as 10. And when I say calculate display, I will be able to see this beam and see all the different properties associated with that beam over here. You see the moment of inertia, everything is calculated and given to you. So you can check if it's all correct. So once this beam library is created, you do OK. And it comes here. You can also click here. You will see you find the existing beam section. The name of the material can also be found from the database. If you click here, you get the material database, you get aluminum. Now, one of the most important things for beams is how it is oriented. So you know that the beam has a certain cross section. Now, if it's an I-section beam, and I don't care about how it's lying in space, then it could also become an H-section beam. Yeah, so it falls on the wrong side. So all the calculations I do based on how the beam cross-section is lying are going to be wrong. And therefore, the most important characteristic, that is the moment of inertia, if that is incorrect, then all my stiffness matrices, etc. will also be incorrect. So I need to define what is the bar orientation. And by means of bar orientation, you can have vector, you can have node ID, etc. Now I'm going to use a vector formulation, and in PATRAN, the bar orientation always is such that the cross section has a vector which is pointing upwards. And that is the one we need to provide. Now we know that we see that according to the global coordinate system here, the bar is along x, but the perpendicular to the cross section is the axis y. So I'm going to put it in space as 0, 1, 0. And for a vector, you have to use greater than, less than signs as the brackets. And the rest of the things we don't need to fill up because it can calculate everything else on its own. You'll see all these areas are grayed out because it calculated everything for you because you defined a section. Now you do OK. You select the application region, which is going to be entities. You can pick up this curve here, which is curve 1. You do add, OK, and then hit apply. And here I'm using this on remote desktop, so I don't see everything. But here you see the property set C-beam is created. Now I want to go back to here on the top to see what else do I need to do. So now I have a beam. I have created the material, I've created the property, and I've also selected the material property to be associated to the section, which is the 1D beam. And now I need to go about meshing it. Or I can also apply load and boundary condition first and then go about meshing it. So let's just do the load and boundary condition. So we see we have to create a displacement boundary condition, which is going to be called fixed. And here we are going to input some data such that it's completely fixed in space. That means it has 0 translations and 0 rotations. And this point that I'm talking about here is a point here, so I can just click on this point entity. So the only thing I pick up in the geometry is the point, which can be curve 1.1 or it can be 0.1, doesn't matter, they are both the same. And I do OK. And once I've selected the application region, don't forget to go down to hit apply. And this boundary condition is already set up. The same way we are going to create a load or a force, which is going to be a concentrated force acting on a node. We are going to name it P, and in input data, we can write where the force is acting. Now we know that F1 is acting in X, F2 is acting in Y, which is the one we need. So it's negative of Y, so minus 100, 0. Select the application region as also a point here. Add OK and hit on apply. So now our load and boundary condition are also set up. The next step is simply to make the mesh. Now for that, we are going to create a mesh seed first by putting one element on the curve. So it creates the mesh seed automatically. Then you have a mesh. We want to make, we don't want to mesh a surface but a curve. So it automatically goes back to a bar 2 element. Here we have to click on the curve that we want the mesh on. We can select an existing property, which is C-beam, and then apply. So when it applies everything to the curve here, you will see that there are some elements that are created, which we can go down here and see one element is associated to the element property C-beam has been created. So now we had applied our boundary condition and displacements to the points, to the geometry. Now in general, it should always also associate it to the node that lies under it. But with PATRAN, that sometimes doesn't work. So the only way to check is to actually run an analysis. We didn't create a load case this time because we are using the default load case. It's quite a simple problem. So I'm just going to analyze the entire model using a full run. I'm going to call it Cantilever beam. And under solution type, I'm going to just keep it as linear static. It's always good to check. Then I'm going to go and check for subcases. See, only default is available, so I don't have to change anything. The subcase selected is also default, so everything is set for running the analysis. Now we'll hit on apply. Now once the analysis runs and finishes after having gone into Nastran, and Nastran being the solver tries to solve the problem, we will get a result. Now whether or not, if the load and the boundary conditions were not applied to the nodes but remained on the geometry, then of course we will not have a solution. And the way to find that out is by going here and trying to attach the XDB file. Once we hit on that and say apply, it tries to attach the XDB file and actually manages to end attaching a results file. That means we do have results. So now we can go on to the results section. We can create a quick plot of the displacements, translational displacements against the translational displacement as a fringe. So you see that there's a certain deformation, and the value of the deformation is something around 1.15. So we can go and look at, instead of magnitude, look at the y component and hit on apply, and we see that the value becomes negative, which is the right in the direction of the vector. Instead of using the quick plot, we can also just check the deformation. Instead of all these colored pictures, you can also just see what the displacement is, not as a resultant, but in component form in YY, and hit on apply, and we see that we get a displacement of 1.15. Now what you can do is you have result for a certain element, and if you keep following, if you go back now to your the particular graph that we started making with the number of elements, then you will see that you can start pointing out what the results are in your graph itself. So I would recommend you also to watch the ABAQUS tutorial, but then switch to the parts where I go back to the slides, and you will see that for one element I can plot the value against the maximum displacement I'm expecting. Now I have the result for one element. I can also now go back to the meshing and say, yeah, but I would like to change the mesh on this now. So I'm going to go back to deleting the mesh completely. So I'm going to delete the mesh, not on the surface, but on the curve. Now I'd say, all right, it's curve 1, apply, it deletes the mesh, and I can go back to creating a mesh seed again. And this time I'm going to use 2 elements. It's going to complain that it already has a mesh seed, you want to replace it, you said yay. And then you have mesh, again the same one, you hit on apply, and this time you have 2 elements. Now when you're creating 2 elements, as I said also in the classroom, you have extra node that is created here. Okay, so once you've created multiple elements, there will be multiple nodes that are lying on top of each other. So what you need to do is you need to check first as equivalence, put a very small tolerance and say, are there any duplicate nodes, and hit on apply. And you will see here in the over here that there was no need to apply any nodes to be deleted. That means there were no equivalent nodes in any section. So here you have only 3 nodes that are created in the 2 elements. So now once you have your new mesh, you can go back to analysis, analyze the entire result again, the exact same way as we did before. And this time we will hope that the loads and boundary conditions are still attached to the same model. And the only way to find out is actually to access the results after Nastran has finished processing it, which I think it has already done. So we can go back to attaching the XDB file, hitting on apply, and here we have end result file. Go back to results, check what the answer is in terms of translation for component Y. Now we see that we still get result 1.15. So you see that if I keep increasing the number of elements, I will see a much smoother transition, but it's not like it's going to change anything in terms of the result. So that means I can use a certain number of elements already for a convergence study that is getting close to the result that I need. Well, I finished the complete analysis with ABAQUS by using 4 elements, 8 elements, 16, 32. In ABAQUS, the element description is slightly different than PATRAN, and it took us some number of elements to get to 1.15, whereas for PATRAN, it automatically got to 1.15 with the way it has been described. So there are some differences, like you see in the kind of element that is used, but I would ask you to continue doing this analysis by changing the mesh a few more times to see okay, do you see a much smoother transition, not a kink like this, and you will see a much smoother bend. So you can check for stresses also along the length, etc.